Now we're going to talk about a more modern kind of cryptography called public key cryptography. All of the encryption schemes that we've seen up to now rely on a symmetric encryption key. That's the key that is known by both the sender and the receiver, and using the one key gives enough information to both encrypt and decrypt a message. So for the Caesar cipher, the key was the shift number S. For the decimation cipher, the key was the multiplication value key K. The linear cipher used both of these for its key, and the Vigenère cipher used a keyword. For this to work, there has to be a secure way for the sender to tell the receiver the key without it being intercepted by a third party. And this can be a problem, especially in modern communication where we want to send private information over the internet. Public key cryptography is what we use to solve this problem. In public key cryptography, there are actually two types of keys, a private key and a public key. The public key is known to everyone, and the public key is what's used to encrypt messages. The private key is known only to its owner, and it's what's used to decrypt messages. So knowing one key is not enough to both encrypt and decrypt the message. If you wanted to send me an encrypted message, I would give you my public key, which you would use to encrypt the message. And then the message can only be decrypted using my private key, which only I know. So even though the public key gives enough information to encrypt, it does not give enough information to decrypt. So this diagram here shows how this process works. We have the original message. The sender uses the receiver's public key, puts it into an encryption algorithm which encrypts the message. That encrypted message is sent to the receiver. The receiver uses their private key in a decryption algorithm to get the decrypted message, which they can read. One commonly used type of public key encryption is called RSA. In the mid-1970s, Rivest, Shamir, and Adelman came up with one of the best known and most widely used public key encryption schemes. And it's named RSA encryption after them, with the first letters of their last names. RSA encryption relies on the fact that it is very hard to factor really large numbers. So this is what makes it a safe encryption scheme. And when we're talking about really large numbers, we're going to be talking about numbers that are hundreds of digits long. So first, a little review. Factoring is reducing a number to a product of prime numbers. So if I look at the number 6, then I can reduce that to 2 times 3. And 2 and 3 are both prime numbers, where prime means it's divisible only by 1 and itself. In another example, if I look at the number 15, I could reduce that to 3 times 5, which are both primes. So let's look at how RSA works. And I don't really expect you to memorize or use this method, but we're just going to go over it to get a general idea of how it works. So don't worry if you have a little bit of trouble following along with this part. To begin with, the data to be sent has to be translated into numerical form. And that's probably going to be a little bit more complicated than what we did, where we just looked up numbers that corresponded to letters in a chart, but the same idea. In this scenario, we're going to call the receiver Alice and the sender Bob. These are traditional names that are used in describing cryptography. So how does this work? Alice has to choose a public key and a private key. So to do that, she's going to first choose two very large prime numbers, p and q. And remember that these numbers are going to be so big that they are hundreds of digits long. She also chooses a number e that has no divisors in common with the number p minus 1 times q minus 1, which means there's no number that divides both e and that product. Then Alice is going to tell Bob both p times q and e, which make up the public key. So Bob knows p times q, but he doesn't know what either p or q by themselves are. For the private key, Alice is going to find a number d so that this equation is true. E times d mod p times 1, p minus 1 times q minus 1 is equal to 1. And this is kind of similar to what was needed to decrypt the decimation cipher. So now she's got her public and her private key. Bob knows the public key, but nobody else knows the private key. Bob can use the public key to encrypt his data. If the numerical form of Bob's data is M, some big string of numbers, then his encrypted data will be C equals M to the power E mod P times Q. So that's going to be another big number. Bob can safely send C to Alice. It's encrypted. And then Alice can use the private key to decrypt Bob's data. And since these are very large numbers, Alice is going to use a computer to find Bob's original data M, which is going to be equal to C to the power D mod P times Q. And now Alice can read the decrypted data. So again, this is based on using modular arithmetic and large prime numbers. So how safe is RSA encryption? Well, the safety relies on the difficulty of factoring very large numbers. So the bigger the numbers you use, the safer it is going to be. So exactly how safe is that? Well, a MIPS year is a measurement of computational steps for computers. One MIPS year is equal to the number of instructions executed during 1 year of computing at 1 million instructions per second. So the actual time this takes is going to depend on how powerful the computers doing the work are. And as computers get more powerful, this will take less and less time. So down here, I've got, if I have a key that is 512 bits, which is 155 digits long, then it's going to take 30,000 MIPS years to crack that encryption. And that's equivalent to a few weeks with a lot of resources, something like a network of powerful computers. If we go up to 768 bits or 232 digits, then that would take a few hundred years with the same resources to break that encryption. And it just keeps going up. If we go up to 1024 bits or 309 digits, then that is more than 1,000 times longer, so hundreds of thousands of years. And then even more for 2048 bits or 617 digits. So the bigger the numbers you use, the better in this case. One place where RSA is used in practice is in keeping the internet safe. Whenever you go to a secure website, usually one whose address starts with HTTPS or has that little padlock icon, the server that hosts the page will send a public key with a certificate to your web browser. If your web browser doesn't recognize the issuer of the certificate, you might get a warning message telling you that maybe this isn't actually safe. The browser uses the public key that it's been given by the website to encrypt a random symmetric encryption key, so a key like the one that we saw in our encryption schemes, and sends it to the server. The server decrypts the new key using its private key, and now your browser can communicate with the server using the new key, which is faster than using RSA. So it uses RSA to securely send a key, and then it uses another encryption scheme that is more like the ones that we saw in the book. Things you should know: you should be able to know the difference between an encryption scheme that uses a symmetric encryption key and one that uses public and private keys. So a symmetric encryption key is enough to both encrypt and decrypt the data. If we have a public and private key encryption scheme, then there are separate keys to encrypt and decrypt the data. You should understand that RSA uses large prime numbers and modular arithmetic to generate public and private keys and encrypt and decrypt data. Also, know that factoring very large numbers is a hard problem that RSA relies on to keep data safe. And finally, understand how secure websites use public and private keys to keep your personal information safe.